Welcome to the Explainer. Okay, let's just dive right into this. Have you ever stood near an airport runway, watching a 300-ton metal tube just effortlessly lift into the sky, and thought about the sheer mind-bending physics making that possible? Or, watched a rocket tear through the atmosphere on a literal pillar of fire? It's just pure harnessed chaos. Today, we're going to demystify exactly how jet and rocket propulsion totally revolutionized travel. We'll trace the mechanical evolution from those first whistling jets of World War II all the way to modern commercial turbofans. And finally, we're going to break down the fundamental thermodynamic laws that actually govern the ultimate power of rockets. It is an absolutely incredible journey of human engineering. So here's our roadmap for today. First up, breaking the speed barrier. Then, the anatomy of jet propulsion, followed by the evolution of jet engines. After that, we'll hit the physics of efficiency, and finally, wrap things up with rocket thermodynamics and thrust. All right, let's kick things off with Section 1, breaking the speed barrier, and specifically, the propeller limit. To really understand why the jet engine was invented in the first place, we first have to understand the massive physical wall that engineers smashed into back in the 1930s. That was the multi-million-dollar question, right? How do you push past the speed of sound when propellers actually hit their physical limits? You see, before World War II, aviation was strictly propeller-driven. But an airplane propeller is essentially just a spinning wing. As aircraft designs got faster and way more powerful, the tips of those spinning propeller blades started approaching the speed of sound, even if the plane itself was flying much slower. And when that happens, shockwaves form. The aerodynamic drag spikes massively, and propeller efficiency literally plummets. Engineers quickly realized that if humanity was ever going to fly faster, a totally new propulsion mechanism was necessary. We had to move beyond the propeller. What followed was a frantic, high-stakes race of invention. In 1928, an RAF cadet named Frank Whittle formally submitted his radical ideas for a turbojet. Completely independently, by 1935, Hans von Ohain started working on a very similar design over in Germany. And this sparked a quiet but incredibly intense race. Ohain's work culminated rapidly, and in August 1939, the Heinkel HE-178 made the world's first purely jet-powered flight. Wow. By 1944, this technology was violently thrust into reality as the German Messerschmitt Me-262 and the British Gloster Meteor entered World War II combat within mere months of each other. This intense, absolute pressure cooker period forever changed the limits of aviation. Moving on to Section 2, let's look at the anatomy of jet propulsion, or basically how a jet breathes. Let's zoom right into the engine itself and look at how an air-breathing jet actually works. At its core, a jet engine is what we call a reaction engine. So a reaction engine generates thrust by emitting a rearward jet of fluid, relying entirely on Newton's third law of motion. You know the one. Every action has an equal and opposite reaction. Whether you're looking at a huge commercial jetliner blowing heated air out the back, or a rocket blasting exhaust into a total vacuum, the fundamental physics are exactly the same. You throw mass backward really, really fast, and the vehicle is pushed forward. It's that simple. But how does a jet continuously generate that rearward flow? Well, it relies on something called the Brayton thermodynamic cycle. Now, the absolutely easiest way to remember this is the simple analogy, suck, squeeze, bang, blow. Let's break that down. First, the intake sucks air into the engine. Second, a spinning compressor heavily squeezes that air, massively raising its pressure. Third, in the combustor, fuel is mixed with this high-pressure air and ignited. There's your bang. Fourth, this expanding, superheated gas blasts through a turbine, which actually spins the compressor at the front of the engine. And finally, the remaining energy exhausts through the propelling nozzle, the blow, giving us our forward thrust. Unlike a car engine that fires and pulses, a jet engine is doing this continuously, creating a massive, uninterrupted river of power. Okay, Section 3. The evolution of jet engines, taking us from turbojets to turbofans. As aviation exploded post-WWI, the basic turbojet we just described really had to evolve. The new problem wasn't just raw speed anymore. It was the incredible fuel efficiency needed for modern commercial travel. Think about it. In an early turbojet, 100% of the incoming air passes directly through that incredibly hot engine core. Now that's great for supersonic fighter jets, sure, but it is highly inefficient and unbelievably loud for regular subsonic flight. To solve this, engineers got creative and created the turbofan.
By adding a massive fan to the front of the engine, most of the air sucked in actually bypasses the hot engine core entirely, flowing around it almost like a cold, protective sleeve. This bypass air yields anywhere between 30% and 70% of the total thrust. This brilliantly illustrates why modern commercial flight relies heavily on high-bypass turbofans. They save just massive amounts of fuel and dramatically reduce engine noise, all while still generating the immense thrust needed for those long-haul flights. That brings us to Section 4, the physics of efficiency, or as I like to call it, the battle between efficiency and power.
Let's zoom out a little bit here to look at the hard data governing engine performance because it sets up a truly fascinating clash between long-haul fuel efficiency and raw, unadulterated power. We measure propellant efficiency using a specific metric called specific impulse, or ISP. Basically, it tells us how much thrust we get for every unit of propellant consumed over time. The General Electric GE90 turbofan, which is used on Boeing 777s, boasts a specific impulse of a staggering 12,080 seconds. Now compare that to a SpaceX Merlin 1D rocket engine, which sits around a measly 310 seconds. Wow. So the crucial point here is this clear trade-off. Air-breathing turbofans sip fuel because they get their reaction mass, the oxygen and air, for absolutely free from the atmosphere. Rockets, on the other hand, they don't breathe air. They have to sacrifice specific impulse because they must carry and burn incredibly heavy onboard oxidizers to achieve maximum speed, and of course, to operate in the total vacuum of space. But hey, rockets have their own major trump card, a mind-blowing 180.1 thrust-to-weight ratio. So while turbofans easily win on efficiency, rockets absolutely dominate on raw power. The Merlin 1D rocket engine can literally lift 180 times its own weights. To put that into perspective, a heavy turbofan might only have a thrust-to-weight ratio of maybe 5 or 6. Because rocket engines use incredibly dense liquid propellants instead of thin atmospheric air, their internal pressures are just astronomical, completely dwarfing traditional duct engines when it comes down to sheer brute force lifting power. Let's head into our final part, Section 5, Rocket Thermodynamics and Thrust. We're going to be visualizing the extremes here. To see exactly how rockets achieve this incredible thrust, we kind of have to slow the pacing down a bit and visualize their thermodynamic cycles. What we're looking at is a pressure-volume, or PV diagram of an ideal thermodynamic cycle for a rocket engine. The vertical axis is pressure and the horizontal is volume. See that line from 1 up to 2? That represents compression. For a liquid rocket, the turbopumps easily push the liquid propellant to a super high pressure. Then the line from 2 to C is the combustion chamber. This right here is where the magic happens. Heat is inputted at a constant pressure as the propellants burn, which massively increases the volume and temperature. Finally, the dramatic curve from C all the way down to E represents isentropic gas expansion right through the rocket nozzle. That heat input transforms directly into kinetic energy. And here's the absolute secret to the whole shebang. The entire area enclosed by that shape, 1, 2, C, E, represents the total mechanical work, or thrust, generated by the cycle. But, what happens when things aren't ideal? Notice how the curve from C down to E stops early here? This is what we call uncompleted gas expansion. It happens when the pressure at the exit of the rocket's nozzle is still greater than the ambient atmospheric pressure outside. Because the nozzle isn't wide enough to let the gas fully expand to match the outside air, the cycle just cuts off. That missing space? That means the area inside the graph is significantly reduced. And since we know area equals work, well, your useful work and your thrust are significantly reduced too. So this brings us to an absolutely crucial engineering takeaway. The absolute peak of cycle work occurs when nozzle exit pressure perfectly matches ambient pressure. If the nozzle pressure is higher, you lose potential energy. If it's lower, the surrounding air literally crushes the exhaust plume inwards, causing drag and severe flow separation. Energy dissipation is just unavoidable in reality. The ultimate key to maximizing a rocket's thrust is perfectly matching those pressures, which, as you can imagine, is an incredibly difficult task considering a rocket is constantly climbing through an atmosphere where the ambient pressure is always dropping. Which really leaves us looking toward the horizon. From Frank Whittle's very first turbojet sketches, to the high-bypass giants of modern commercial travel, to the utter thermodynamic perfection required to throw heavy rockets into orbit, human engineering is just a relentless pursuit of efficiency. But as we keep pushing the boundaries into hypersonic scramjets and even nuclear thermal rockets, we really have to ask ourselves, what is the absolute, ultimate limit of thermal to mechanical energy conversion? Just how far can the laws of thermodynamics actually take us? It's a massive question, and one that engineers are trying to answer every single day. Thank you so much for joining me on this explainer, and hey, keep wondering what's possible out there. If you found this explainer helpful in grasping the complex and fascinating engineering, like, share, and subscribe to @MakersJunction on YouTube for more highly professional, basic to advanced engineering content. Keep exploring, keep building, and we'll see you in the next explainer.